Neural networks run on matrix math, but before an algorithm can start training, it has to move through your data architecture. If those dimensions don't line up, the code crashes. Mismatched shapes are the most common source of errors for beginners working in PyTorch. To prevent this, we inspect the data before attempting an operation. We'll start by setting up our coding environment, importing PyTorch, and defining a basic two-dimensional tensor matrix. Calling shape returns exactly how many rows and columns exist in the tensor. Here, we have 2 rows and 3 columns. To know the total axes, run the dim command. Highlighting the clear x and y-axis confirms this is a 2D matrix. Extracting the shape and the total dimensions ensures you know exactly what memory blocks you are holding. That baseline verification is the first step before attempting any mathematical manipulation. Once you know your baseline, you often need to alter it to feed into a specific network layer. PyTorch handles this with the view command. We can take our existing 2x3 matrix and view it as a 3x2 matrix instead. This animation illustrates why the total number of elements must stay exactly the same. PyTorch is efficient. It doesn't copy the data. It simply reads the original 6 items from memory and wraps them sequentially, left to right, into the new boundary. Because the total element count is strictly enforced, you can pass a -1 as a wildcard. If you request 2 columns but leave the row count as -1, PyTorch calculates the missing dimension based on your 6 starting elements, snapping them into 3 rows. Sequential wrapping isn't the only way to get a 3x2 output. The transpose command takes a different mathematical approach. Instead of reading left to right, transpose swaps the axes physically, flipping the entire matrix over its diagonal. View pushes elements down to the next row when it runs out of space. Transpose takes the entire first row and turns it into the first column. Both operations result in a 3x2 shape, but the location of every data point inside that shape has changed. Choosing between reshaping and swapping alters the mathematical meaning of the matrix data. The most common operation you will run on these matrices is multiplication. In PyTorch, you execute this using the matmul function, or the Python @ symbol. This formula shows the mathematical requirement for matrix multiplication. The inner dimensions of your 2 tensors must match. If you have an m by n matrix, it can only multiply against an n by p matrix. Let's test that against our data. If we multiply our original 2x3 matrix by the transposed 3x2 matrix, the inner 3's align. They cancel each other out during the calculation, producing a 2x2 output matrix. Now let's try it with a challenge. We have tensor x measuring 2x3 and tensor y measuring 2x4. When we attempt to multiply them, we hit a stop. The inner dimensions of 3 and 2 reject the operation. Pause the video right here. Look at the tools we've covered and determine which command you need to apply to tensor x so this multiplication executes. The solution is transpose. By calling transpose on tensor x, it swaps the axes, returning a 3x2 matrix. The inner 2's now align and multiply against tensor y to produce a 3x4 result. Spatial awareness of inner dimensions is the primary requirement for executing matrix operations within a neural network. There is one final trap in PyTorch linear algebra. Programmers coming from other frameworks frequently try to use the dot command for standard matrix multiplication, which leads to immediate errors. This split diagram shows the distinction. In NumPy, you can use dot for 2-dimensional matrices. PyTorch follows the strict definition. Torch dot calculates the inner product of 2 1D vectors only. Attempting it on a 2D matrix throws an error every time. This cheat sheet outlines your core toolkit. Use shape and dim as inspection tools to expose the exact length and axis count of your starting tensor. When you need to adjust structure, use view to push elements sequentially into a new frame, or transpose to swap the underlying axes. For mathematics, matmul handles standard matrix multiplication for 2D tensors, while dot is reserved for 1D vectors. Internalizing these 5 commands provides the foundation for debugging matrix logic. When you can verify dimensions and swap axes reliably, you are prepared to handle the standard linear algebra operations that define most neural network layers.